Welcome to my channel again. I hope you might have enjoyed my previous chapter lectures on the previous chapter, that was of quantum mechanics. So today I am going to start a new topic, that is of laser, and in the today's lecture I will be discussing primarily with you the Einstein's theory of radiation. First of all, let us now define and understand what is meant by this word laser. Okay, like laser, actually it contains 5 alphabets. Initially it was the compressed form of a sentence in which each alphabet meant something. Means actually laser was an acronym for this, like this. But nowadays we can write laser as this also. It has become a noun now, and even we can use these words like lasing, which now represent process. However, initially we go historically, laser meant to be acronym for a sentence. What was the meaning? Meaning of this, in case of this laser, L stands for light, then A stands for amplification, S stands for stimulator, E stands for emission, and R stands for radiation. And we will add these two words from ourselves: light amplification by stimulated emission of radiation. So the full form of laser therefore can be summed up as follows. This is the full form of laser: light amplification by stimulated emission of radiation. So this is the full form of the laser. Now we can turn our attention to what is the definition of the laser. So the definition of laser is, it is an optical device. Laser is an optical device which can produce monochromatic, intense or focused, and rather, instead of, you can also use intense or focused or directional, and coherent beam of light. So as it is clear in the definition of the laser, the 3 properties which are distinctive of a laser are the monochromaticity, its intensity or directionality, and the coherence nature of the light. Normally the sources of light, which are natural sources of light or man-made sources of light before lasers, they were not emitting light in one direction. For example, all natural sources of light emit light in all directions. Sun is the most prominent source of light in our lives, in our life. And for example, then man-made sources include light sources like a bulb or a tube. So in case of a bulb, the light is emitted with the help of spherical wavefronts, and in case of tube light, the light is emitted in the form of cylindrical wavefronts. But in case of lasers, the wavefront is always a plane wavefront because light is directional and it doesn't spread. So this is the definition of the laser. To understand how a laser works, what are the principles behind the working of a laser, we must have the knowledge of very important theory, and I will shift my attention to that article. This article is named as Einstein's theory of radiation. Okay, Einstein's theory of radiation. So, what is there in this theory? Suppose I have a certain material which I am using for, let us say, obtaining stimulated emission. So, let us say this is the lower energy level. I will call it to be ground energy level. Its designation will be G. Let the average energy of this level is E1. And let us say this is the higher energy level. This energy level is called excited energy level. I will designate it as E, and I will give its energy value as E2. Okay, now there are many electrons which are in the ground level, and we want to excite this these electrons from ground level to the exciter level. For that we need energy. Let us say there is a beam of radiations incident on the material, and by absorbing this energy, certain electrons jump from lower energy state G, lower energy level G, to higher energy level E. Suppose let us say N1 is number of atoms per unit volume in state E1, and N2 is number of atoms per unit volume in state E2. Obviously N1 and N2, both of them will have unit of per cubic meter, reciprocal of the unit of volume, because number of atoms will not have any unit. Now these electrons will jump up by absorbing this energy. So out of this beam of photons, this is a polychromatic light initially. So it means all the photons which are in this beam are not of same energy. So the photons which will show maximum absorbance will be these one. Let us say a photon has frequency nu in this beam, and if this photon satisfies this equation, h nu equal to E2 minus E1, I will call this as equation number 1. Then such a photon will have maximum probability of being absorbed by the material, and such a photon will result in the transition of an electron from ground level G to the excited level E, because the energy difference E2 minus E1 between G and E exactly matches with that of the energy of the photon. Such a photon will be called as resonating photon. and such a photon will be responsible for the excitation from G to E. Okay. Now let us now move ahead. The state E, which is an excited state, is short-lived. Its lifetime is of the order of 10 raised to power minus 8 seconds. So the electrons which go to the excited level E, they can stay there only for, on the average, this much amount of time. So after that, these electrons have to leave this state. So when these electrons will leave this state, they will jump back to this state if there is no other intermediate state. I am assuming for the time being, I assume that there is no intermediate state between G and E. So these electrons will jump back to this state. So when they will jump back to this state, then according to Einstein, they can jump back in two manners. One method is called spontaneous and other is called stimulated. I will use the abbreviation SP and ST, spontaneous and stimulated. What happens in case of spontaneous emission? So let me just give you the definition of the spontaneous emission. So it is a random process and electrons will jump down to the ground level after spending their lifetime in the excited level, and when these electrons jump down, the electrons are not taking the energy from any external source. So no external energy is required for such a process to take place, and since the electrons are just randomly de-exciting, so therefore the photons emitted will have different directions. Although they will have the same energy, because all of these are traveling from because all of these are de-exciting from E2 to E1, so the energy of all these photons will be E2 minus E1. However, the directions between these photons will be varying from one to another. So these photons will not be traveling in one direction, so and obviously these will be non-coherent. On the other hand, the second process, that is stimulated process, stimulated emission is an ordered emission. This emission does not take place automatically. It requires external energy and any external photon which will create this process should have the energy. This external energy of the photon should be same as that of the photon which is going to be emitted, that is E2 minus E1, and the emitted photons will travel in a single direction and will possess coherence. So this is the important part in the second kind of emission, that is stimulated emission, that the photons stimulated emission, it requires external photon, and the external photon will start a process in which the emitted photons will be in the direction of external photon. All these photons will have same energy, same direction, and these will be coherent with each other. So that is the difference between spontaneous and stimulated emission. Okay, now I am going to erase this. So, since this beam which is incident on the material, it is polychromatic, so therefore I would define a new parameter, that is rho nu. Some books write it as u nu, but I would rather prefer it to use it as rho nu. So what is this? It is energy density of the incident beam for a given frequency, per unit frequency. Obviously, energy density will have unit joule per cubic meter and frequency will have unit hertz. So therefore, this unit becomes joule into second per cubic meter. So it means in this beam, all photons, let us say there are 100 photons in this beam, and there are 10 different frequencies, then it does not mean that all frequencies have equal number of photons. Means you cannot say there will be 10 photons of frequency nu 1, 10 of nu 2, 10 of nu 3. We cannot say. There may be more photons of one frequency as compared to other. So therefore the distribution of energy in this beam for all photons is not the same. So that is why I have written energy density per unit frequency. So this parameter rho is a function of nu. Different frequencies will have different energy density. Okay. Now let us assume that Ra is rate of absorption per unit volume of the sample, and Rst is rate of stimulated emission per unit volume of the sample. Rsp is rate of spontaneous emission per unit volume of the sample. All these three will have same unit, that will be it is the rate, that is 1 rate of absorption, number of photons absorbed per unit second per unit volume. So the unit of all these three rates will be second inverse and meter raised to power minus 3. So this will be the unit of rates. Now what, according to Einstein, the rate of absorption Ra is directly proportional to N1 and nothing else. Means if there are more number of atoms in the ground level, then there will be more absorption. So if I want to convert, it is also directly proportional to rho nu. So if there are more number of atoms in the ground state, then there will be more absorption. Similarly, if there is more intense beam of light for a given material having N1 atoms in the ground state, if there are more intense, if there is more intense beam of light having particular frequency nu, and the desired frequency nu is given in equation 1, that is E2 minus E1, then the rate of absorption will be increased. So if I want to convert this proportionality into equality, I can write it like this: Ra proportional to N1 rho nu, or I can write Ra is equal to B1 to N1 and rho nu. This is my equation number 2. Here B12 is constant of proportionality, and it is called Einstein's coefficient. absorption. So this V12, if we know the unit of Ra, we know its unit is second inverse and meter power minus 3. I can find the unit of V12. It is second inverse meter minus 3. V12 unit I want to find. N1 unit is meter power minus 3. Rho nu is joule into second and meter power minus 3. This meter power minus 3 will get cancelled here, and therefore V12 unit will be joule minus 1, second minus 2 and meter 3. This will be the unit of this coefficient V12. You can verify it. So next is, this is the rate of absorption. Then we want to find the rate of emission. However, emission is of two types. One is spontaneous and another is stimulated. So we need to find the rates of both of these equations. So what is the first equation? So according to Einstein, the rate of spontaneous emission, since spontaneous emission is a random process and it does not require any external photon for this process to start, so therefore it is a function of only number of atoms in the excited state, nothing else. That is, more will be the number of atoms in the excited state, more will be the spontaneous emission. So I want to convert this proportionality into equality. I would get RSP is equal to A21 N2. This is equation number 3. Here A21 is again constant of proportionality and it is called Einstein's coefficient for spontaneous emission. So it is very easy to verify that the unit of A21 will be second inverse or hertz. You can verify it. Here I have written 1, 2. Here I have written 2, 1. It is just to indicate that this process is from state E1 to E2. It is an upward process, that is absorption, and it is a process from E2 to E1, that is downward process, that is emission. Similarly, we want to write expression for rate of stimulated emission. According to Einstein again, rate of stimulated emission is proportional to two variables. One is N2, it has to be there. Any kind of emission, whether it is spontaneous or it is stimulated, cannot take place if there are no atoms in the excited level. So therefore, both RSP and RST must be proportional to N2. The only difference is that it requires external energy. So therefore, the additional variable over which RST depends is external energy density rho nu. So just as we have formed the relation 2 for absorption, in the same way I can form the relation for stimulated emission. I do not need this part of the diagram. I am going to erase it. So if I want to convert this into an equation, firstly I would write IRST proportional to N2 rho nu, and when I will convert this into equation, then I will get RST is equal to B21 and N2 and rho nu. This is equation number 4. Here B21, there I wrote B12, here it is B21. So 1, 2 and 2, 1 principally tell the difference between the process, nature of the process. 1, 2 tells it is in the absorption process, 2, 1 tells it is in the emission process. This B21 is called Einstein coefficient for stimulated emission. It is very easy to verify, just as in case of B12, that unit of B21 will be same as that of B12, that is joule minus 1, S minus 2 and meter cube. Okay, Now what we are going to do? So for that I am going to give you small demo. Suppose this is our material. Kindly remember, this is the energy level diagram of the material. Let us say this is the sample of the material. It contains a number of atoms. Initially at t is equal to 0, when we started the process, then all atoms were in the state n1. So n1 was maximum and n2 was 0. If you see equation number 2, 3 and 4, unfortunately I have just erased equation number 2. You can see that since n2 is involved in involved in RSP and RST, and initially n2 is 0, therefore at t is equal to 0, both RST and RSP will be 0, and RA, since it involves n1, it will be maximum. So what is going to happen when I will put incident light on the material? Let us say the incident light is coming from left side. Then initially, since all atoms are in the ground state, so the rate of absorption will be maximum and rate of any kind of emission will be 0. So the material will preferably absorb light. When material will absorb light, and if you can appreciate this from this diagram, that absorption means n1 will decrease and n2 will increase, because electrons are showing transitions from state E1 to E2. Therefore what will happen, as time will pass, this upward arrow means t is increasing. As time will pass, what will happen, the value of n1 it will decrease and value of n2 it will increase. So what is the meaning of this? Its meaning is that RA it will decrease from maximum value, while RSP and RST they were initially 0 value and they will start increasing. So the total rate of emission is actually RST plus RSP, and total rate of absorption is actually RA. So as we will be putting light on the material, initially material will only absorb light, but as the time will pass, it will also start emitting light. So the rate of absorption with time will be decreasing and rate of emission with time will be increasing. And at thermal equilibrium, what is going to happen? At thermal equilibrium, these rates will become equal. At thermal equilibrium, the rate of absorption, that is forward, just as we say in chemical reactions, at equilibrium the rate of forward reaction is equal to rate of backward reaction. Here I will say rate of absorption will be equal to rate of emission, that is RST plus RSP. Now we can put the values of RST and RSP and RA. And RA, we know that it was N1, it was B12, N1 rho nu, RST was B21, N2 rho nu, and RSP is A21 and N2. Now we can collect these terms on one side, where we will take out rho nu from common from both of these. So the rho nu is taken out. It will become B12 N1 minus B21 N2 is equal to A21 N2, and rho nu will be equal to A21 N2 upon B12 N1 minus B21 N2. Now we are going to divide on the right hand side numerator as denominator by this factor. When we are going to divide by this factor, it will become A21 N2 upon B12 N2 upon B12 N1 upon it was B21 N2 B21 N2 and minus 1. So this will be the relation. Now I would call this as equation number 5. This is equation number 5. Now we have this relation in our classes that the number density of electrons in a level having energy E at a given temperature T is proportional to this factor. Kindly remember here K is Boltzmann constant. So if this equation is assumed to be applicable here, then N1 upon N2 will become e raised to power minus E1 by KT upon e raised to power minus E2 by KT. The constant of proportionality which will come here will get cancelled out. I assume that both of the states E1 and E2 belong to the same material. In that case, this constant will be same for both N1 and N2. So when I will take it, so this will, when it will go up, it will become plus E2. So it will become e raised to power E2 minus E1 upon KT, or it will become Ny by N2 is equal to e raised to power, since E2 minus E1 is equal to h nu, you can see equation 1 which I just erased, it will become e raised to power h nu upon KT. Let us say this is equation number 6. So now I have the value of N1 by N2 which is equal to e raised to power h nu by KT. I can put this value of N1 by N2 in equation number 5. So equation number 5, it will become, now this is equation number 5, therefore our equation number 5 will become rho nu is equal to A21 upon B21, this N2 and N2 will get cancelled, upon B12 upon B21 e raised to power h nu by KT and minus 1. Let us say this is equation number 6. So I can erase all these equations now because this is the most updated equation with me now, equation number 6. I will move ahead. I will not be needing any equations derived before it. Now we must remember some topic from black body theory radiation. According to black body theory radiation, according to theory of black body radiation, the energy density per unit frequency rho nu is given by 8 pi h nu cube by c cube upon e raised to power h nu upon KT minus 1. This is equation number 7. This is a standard result which I will advise you to just remember for the time being, because it is a part of the statistical physics which I am not going to cover. So kindly remember it. If you are interested, then you can see the proof of this equation in any standard undergraduate book of statistical physics. Here C is speed of light in vacuum, h is Planck's constant, and kindly remember that this part, exponential, is not a rational part, it is an irrational part, and this part in the numerator is a rational part. Now if we compare equations 6 and 7, both of these equations can be compared, then on comparison I can equate numerator of 6 and 7 separately and the denominator of 6 and 7 separately. It is because of the fact that numerator of this equation is rational and denominator is irrational, and whenever an equation contains rational as well as irrational parts, then rational parts are separately equal and irrational parts are separately equal. So kindly remember this. So on comparison of 6 and 7, I will get two equations. So comparison of numerators will tell me that A21 upon B21 is equal to 8 pi h nu cube upon c cube, and or I can write B21 is equal to c cube A21 upon 8 pi h nu cube. This is equation number 8. Now when we compare equation number 6 and 7 for denominators, then you can see 1 is here in both of them, minus is here in both of them, e raised to power h nu by kt is here in both of them, but its multiplier is 1, its multiplier is b12 upon b21. So the coefficients can also be equated. So therefore the coefficient of e raised to power h nu by kt here is b12 upon b21, and similar coefficient here is 1. So therefore this ratio has to be equal to 1. This means b12 is equal to b21. Okay, now this up to this point we have to do certain now discussion. Now what is important for us, what conclusions we can make from here? I am going to erase this diagram right now. What conclusions can we make? So first of all, let us go to this equation RA. It was equation number 2. It was equal to B12 N1 rho nu. Suppose I want to give the physical significance of B12. What is the physical significance of this constant coefficient, Einstein coefficient B12? Suppose I have a material for which N1 and rho nu is same as compared to another material for which N1 and rho nu are same, but however both of materials have different value of B12. So when I keep value of N1 and rho nu same for different materials, then I would be simply saying that the rate of absorption will be more in a material in which B12 is large. Therefore, I can just get the significance of B12 that for large values of B12 there will be more absorption of light, and for small values of B12 there will be less value of absorption of light. For example, if B12 is 0, you can appreciate that whatever is rho nu means you can put any amount of intensity or any frequency on a material or having any density of the material. If B12 is 0, then Ra will be 0. Such a material will not absorb any light whatsoever is the case. So therefore B12 tells us the probability of absorption. In the same way, we can appreciate that A21 represents probability of spontaneous emission, and B21 represents probability of stimulated emission. Now, if we have this first-hand knowledge with us, then we can understand what these equations, equation 8 and 9, signify. If we see equation number 8, we see that V21 is inversely proportional to nu q. Now we know that V21 is a probability of stimulated emission and nu is the frequency. This tells us that a given material will have more probability of stimulated emission for smaller frequencies, and as the frequency will increase, the probability of stimulated emission will be decreasing. Therefore, we can very easily say that for a given material, it is possible to get laser emission, which is stimulated emission. It is possible to get laser emission or directional light easily for smaller frequencies or longer wavelength as compared to higher frequencies or shorter wavelengths. Now in the visible range, if we see in the visible range, the wavelengths are written like this, Vibgyor. So the smallest frequency in the visible range is with red region, and this is highest frequency. So if for any material it is easy to obtain stimulated emission for red region as compared to blue region, because blue is the primary. Instead of talking about violet and indigo, I talk about blue region. So therefore the red region lasers would have to be invented earlier as compared to the lasers emitting stimulated emission in the blue or green region, and that indeed was the case. In the visible region, the first ever laser that was invented was the ruby laser, and the wavelength of this light, ruby laser light, was 6943 angstrom, and it falls in the red region of the visible spectrum. Similarly, now what we can get from here, we see that the probability of absorption, this is the probability of absorption, if we remember these significances, the probability of absorption is equal to probability of stimulated emission. Therefore, the materials which absorb light strongly at a given wavelength will also emit light strongly at the same wavelength when the circumstances for emission are, or conditions for emission are met. This is nothing but actually mathematical representation of Kirchhoff's law of optics, which we have already studied in our lower classes. In the Kirchhoff's law of optics, we say that a material at a given wavelength, at a given temperature will emit only those wavelengths which it has absorbed at the same temperature. Now I will move ahead and derive further conditions for stimulated emission. What is this? Now we know that R A is equal to B12 N1 rho nu. We also know that R S T is equal to B21 N2 rho nu. We know that our SP is equal to A21 and N2, and moreover we also know that B21 is equal to CQ A21 upon 8 pi h nu cube. This is the equation that I have just written, and we also know that B12 is equal to B21 1. Now I have written all the important expressions on the board. Now I remember this was equation number, I think, 2, this was 3, this was 4, this is 8, and this is 9. Now we know that we are studying the topic of laser, in which we are trying to understand what are the conditions under which stimulated emission can be made from a material or from a substance. Now, out of these two emissions, I must, or all of you who are attending my lecture, you must appreciate that for the material to give stimulated emission, this ratio should be much greater than 1. Only then stimulated emission can take place. Now, RST or RSP, this ratio must be greater than 1. If I put these values from 3 and 4, you would get B21 upon A21, N2 and N2 will get cancelled. Rho nu should be much greater than 1. Now, from equation number 8, you see B21 upon A21 is nothing but C cube upon 8 pi H nu cube. So therefore C cube upon 8 pi H nu cube, and the value of rho nu from theory of black body radiation we already know. I have erased that value, but I remember its expression. It was this one. This value must be greater than. Now these are cancelling quantities. Therefore, 1 upon e raised to power hc by lambda kt minus 1 should be much greater than 1. I have used the expression nu is equal to c by lambda because most of the times we are familiar with the wavelength values rather than frequency values. Now, how it is a simple mathematics, how this quantity can be greater than, much greater than 1. Since the numerator of the left hand side is 1, so therefore this quantity can be much greater than 1 only if e raised to power hc by lambda kt minus 1 is much smaller than 1. If I take it on the right hand side, in the next step I can write that this quantity must be smaller than 2. Now if I take natural log on both sides, then e raised to power sorry, this is hc upon lambda kt should be much smaller than log 2. So log e we know that 1, this power will come ahead. So hc by lambda kt will be much smaller than log 2, or we can write that t must be much greater than hc upon lambda k log 2. So this is the condition. This is the temperature that we require for stimulated emission to dominate over spontaneous emission. Now we know that H is a constant. It is 6.63 into 10 raised to power minus 34 joule into second. C is a constant, 3 into 10 raised to power 8 meter per second. K is a constant, 1.38 10 raised to power minus 23 joule per Kelvin, and log 2 is a very simple expression. The only thing that we have to decide is lambda. Since I am talking about visible region actually extends from 3500 angstrom to 7500 angstrom approximately, because different books give different wavelength range for visible region. So let us say we are interested in making a laser in which the wavelength of the output light is in just the middle of this region. Let us assume I know the value for 5000. Let us say I put lambda is equal to 5000. This is my desired value. You can make the calculations for different wavelengths also. So if you put all these values here, and put lambda is equal to 5000 value, you can very easily see that temperature must be greater than 33,000 Kelvin. Now this is a surprisingly very high value of the temperature. Why? Because kindly remember that this is not the temperature of the bulk, it is the surface temperature. It is the temperature of the surface of the material which is going to emit stimulated light. So kindly remember the surface temperature of sun is approximately 5800 Kelvin, and this 33,000 Kelvin is therefore much greater than the temperature of the sun also. So this is some condition which tells us that it is not going to happen that we may obtain stimulated emission from a material just by increasing temperature. Since all natural sources of light are giving energy according to Prevost theory, you might Google it on the internet. What is Prevost theory? I am not going to explain it, just I am going to use it, that the emission rate of a body depends upon the temperature difference between the surrounding and the temperature of the surface of the body. Now it means that emission, natural emission from a substance is due to its temperature. So therefore this result just tells me that it is not possible to achieve stimulated emission from a substance just by heating it. If you want to get this result, the temperature must be not only 33,000 Kelvin but many times of it. Let us say 5 times of it. It will make just 1.5 million Kelvin temperature at the surface of the body. Such a huge temperature at the surface of the body is not principally achievable in the laboratory, because it is not just obtained even on the stars. For most of the stars this condition is not met. So therefore we can conclude that the natural sources of light like all stars or sun will not be emitting stimulated radiation. They are dominant. For them this T is much smaller than 33,000 Kelvin. Therefore this ratio which we want RST upon RSP to be much greater than 1 is actually much smaller than 1 for natural sources of light. Therefore natural sources of light are chiefly emitting light in a spontaneous manner, which is therefore polychromatic light, which is non-coherent light, and which is emitted in all possible directions. That is the reason natural sources of light are emitting light with spherical wave fronts. Okay, next I will move to something different. Now we can divide equation number 3 RST with equation number 2 RA. So for good stimulated emission we must have this ratio again much greater than 1. If I put the value of RST and RA from 3 and 2, the left hand side will become B21 and 2 rho nu, and this will become B12 and 1 rho nu. This rho nu will get cancelled, much greater than 1. Now B12 and B21, these are equal according to equation number 9, so these will also get cancelled. Therefore I would get N2 upon N1 much greater than 1. Therefore this will give me N2 much greater than N1. This is giving us some respite. So this is giving us some indirect condition that how you can get stimulated emission dominating the spontaneous emission. So for that, the N2, you kindly remember, N2 is total number of atoms per unit volume in the excited state, and N1 is number of atoms per unit volume in the ground state. So I want N2 much greater than N1. Such a state is of the material is called population inversion. This condition is called population inversion condition. So what is population inversion? When number density of atoms in excited state is much greater than number density of atoms in ground state. Then such a state of the material is called state of population inversion. So this is the first condition that must be met, that material must be in the state of population inversion. However, we know that under certain circumstances at thermal equilibrium, we know that although rate of absorption is equal to rate of emission, I have written REM. REM is actually sum of both spontaneous and stimulated emission. At thermal equilibrium, RA is equal to REM. However, N1 is greater than N2, and we want N2 much greater than N1. So therefore this condition can be obtained only by breaking thermal equilibrium. So we must break thermal equilibrium, and we have just seen that we cannot do such thing by increasing the temperature. Therefore we must do this by some other means. And what is that? We must provide external energy to the material so that this condition is achieved. So therefore this condition N2 much greater than N1 cannot exist by itself. So it is not a naturally occurring state. So we have to break the thermal equilibrium, and that we can do. We must supply external energy to the material. What it will do? We have just seen that when we supply energy, then the rate of absorption increases and N2 starts increasing. At thermal equilibrium, RA and REM are equal, but still N1 and N2 hold this relation. We want to topple this relation. We want N2 at this side and N1 on this side. For that, even when thermal equilibrium is achieved, we should not stop providing external energy. We continue to give external energy so that N1 and N2 interchange their positions and N2 becomes much greater than N1. When it will happen, then the state of population inversion will be achieved. So therefore, the population inversion, which was the first condition, implies a second condition, that we must supply external energy to the material continuously. Because as soon as we will stop the supply of external energy, the material will come back into the thermal equilibrium, and again N2 much greater than N1. This state will just vanish and material will again achieve the state n1 greater than n2, and stimulated emission will not be dominating, spontaneous emission will start taking place. So therefore we have the second condition to take place. What is that? It is that the material must be supplied external energy continuously, and such a process of supplying external energy to the material so that population inversion is achieved and maintained is called pumping. So today we have just got the knowledge of laser, its definition, and we have just discussed Einstein theory of radiation. This topic mathematically it is over. I have derived two conditions. One is that population inversion must be there. Second is that pumping is there. But these two conditions combinedly do not produce a good laser output. There is one third condition also which is necessary. So I will discuss that third condition in detail with you in the next lecture. So till then I will stop here, and I will hope that you will just enjoy my lecture for today, and we will discuss more on the third condition related with the laser in the next lecture. Till then, thank you. Thanks a lot.